Welcome to the final lesson of rates of reaction. This is lesson 10 and we're looking at altering conditions. This is for the AQA GCSE chemistry course. The specification links are shown on the screen. If you are studying from a different exam board, then please check with your exam board specifications that the content of the video is suitable, and check if there's anything else you need to know as well. So students from the school where I teach, these are the lessons, these are the resources for the lessons, so you might do some of these when you're at school. The book references are there for you as well, and if you've got one of the revision guides at home, the book references are there for those too. As usual, I'd like to start the lesson with some pictures, and so you can see the link between the pictures. The video version of this, you'll know what the title is of the lesson already. But in the classroom, we would like to have a guess at what it might be. So pause the video now and see if you can work it out. Well done. Hopefully you've realised that this first picture is an altar, okay, in the church. And then the second picture there is a ring. And then finally we've got some kind of clip art pictures of some different weather conditions. Right, so the title here will be altering conditions. Right, so the AQA specification details are outlined here. Pause the video to get a closer look at those and to read through. Right, learning outcomes. This is a higher topic, okay, which is why there's no targeting grade 4 outcomes there. So pause the video to look at those outcomes in more detail. Okay, so what do we know already? What have we... All right, so thinking back, what conditions can we change in order to affect the rate of reaction? So essentially, what different variables have we looked at through this course, this rates of reaction course? What variables have we looked at that we can use to change rate of reaction? Good, hopefully you've come up with temperature, pressure, concentration and catalyst. Surface area is in there as well, but surface area, we're not changing the conditions really, we're just changing the our reactant's surface area, whereas temperature, pressure, concentration, catalyst, that's actually manipulating the conditions themselves. So I've left surface area out. So what effect will changing these conditions have on rates of reaction? So there's a bit of revision here, so just pause the video and see if you can remember how these different things affect rate of reaction. Good. Temperature, so increasing the temperature increases the rate of reaction, and this is done because the particles will move faster and will collide more frequently, but also the particles are moving faster, so more particles have the activation energy. With pressure, if we increase the pressure, it's going to increase the rate of reaction. So by increasing the pressure, it means there's more particles per unit volume, and that means that they will collide more frequently, increasing the rate. Concentration and pressure go together. The answers that you'll use are virtually exactly the same. So increasing the concentration increases rate of reaction. There are more particles per unit volume again, and the particles will collide more frequently, increasing the rate of reaction. And we've just looked at catalysts, we've just been talking about catalysts. So using a catalyst increases the rate of reaction, provides an alternative pathway with a lower activation energy, and a higher proportion of particles have sufficient energy to react. Well done if you're managing to answer these questions on your own. Okay, that does mean that you've learned a considerable amount. So with our reversible reactions, where the reaction goes both ways, will changing these conditions, will it have the same effect? Will it always give us more yield, or will it always increase the reaction we want? Because remember, the reaction is going both ways. Okay, so if we do something to one reaction to get more of that, it's likely that we'll be getting less of the other one. Okay. So changing conditions in a reversible reaction. We looked at this principle in the last lesson, Le Chatelier's principle, and it tells us about the changing the conditions in a reversible reaction. So Le Chatelier says that whenever a change in conditions is introduced to a system at equilibrium, the position of equilibrium shifts to cancel out the change. Now this sentence is complicated. If you don't have a good understanding of reversible reactions, then this can be confusing. Okay, so what it basically means is, if we change the conditions in our equilibrium reaction, it's either going to make more product or more reactant in order to counteract that change that we made. Now, the language that's used here, so stating the position of equilibrium, is just a way of indicating which of the reactions is more dominant. So we'll run through examples. We've done this before, but we'll go over it again as it's useful. So if we say the position of equilibrium shifts to the right, then that means it favours the forward reaction, the one going to the right, and therefore we get more product. If we say the position of equilibrium shifts to the left, then that means it favours the backwards reaction, okay, the one going to the left, and we get more reactants. Okay, so remember, this is a closed system, and so we haven't got anything escaping or anything new coming in. Right? All we're doing is we've got this closed, sealed container, and we're changing the conditions in there. So what we can do is make that container smaller or bigger, and that would change the pressure, or we could change the temperature of that container, or we could actually start off with the catalyst in there and then seal it. Okay, and these are all the ways that we change those conditions. All right, so let's look specifically then at changing the concentration. So we've got our reversible reaction here, and we've got two lots of A are going to react with B to give me one lot of C and 3 lots of my D molecule. So we could say two moles of A react with 1 mole of B to give me 1 mole of C and 3 moles of D. All right. So what will happen if I increase the concentration of the reactants? So if I increase the concentration of A and B, what's going to happen to my position of equilibrium? How is my reaction? So Le Chatelier is telling us that the position of equilibrium is going to shift to oppose that change. How could I oppose that change? How could I get the concentration of A and B back down to where it was? Okay, think about that. Think about how I could get the concentration of A and B lower. What could happen in my reaction? What could I favour? Would I favour the backward reaction, which would make more of A and B, or would I favour the forward reaction, which would make more of C and D? Excellent, well done. So because we've increased concentration of A and B, the system is going to oppose that change. And so what it's going to do is the position of equilibrium is going to shift to the right, okay, to make more product, okay, and therefore the concentration of A and B will go down again because they've been used to make C and D. So we've opposed that change that's come in. Okay, so look at the language we've used there. So, for example, in a question, it's say, the exact question there, what will happen if we increase the concentration of reactants? And the way you need to answer is the position of equilibrium will shift to the right, favouring the forward reaction to make more product. Okay, so you get a higher yield. So this is one way you could get a higher yield, is by increasing the concentration of your reactants. These are pretty tricky, guys, so if I were you, I'd be pausing that video and I'd be making some notes on each one of these slides, okay, and just adding in, I'd use a whole page, do it on a big whole A4 page if you can, with changing pressure across the top, with the equation in the middle, and then put the notes around the outside. All right, So we've got the same equation here, and this time we've just put some state symbols in, so they're all gases. So if a reversible reaction involves changing numbers of gas molecules, altering the pressure can affect the equilibrium mixture. Now then, earlier on, right at the start of this lesson, that one of the questions was how much space, what volume of space does a mole of gas, a mole of any gas occupy? And that was 24 decimeters cubed. So we've got 2 moles of A, so that's going to occupy 2 times 24, okay? That's going to give us our 48 decimeters cubed. And then B is going to be 24 decimeters cubed. C will be 24 decimeters cubed. And then D here is going to be 3 lots of our 24. That's at 72 decimeters cubed. Okay, so you've got to think about the volume of space that each one of those species in our reaction is occupying. Okay. So what will happen if we increase the pressure of the system? So increasing the pressure, think about that, about making that room smaller. Okay, so we're making that room smaller. There's not as much room in there. So is that going to favour the side of the reaction that's going to make stuff that takes up more space, or is it going to favour the side of the reaction that takes up less space? Excellent, well done. So if we look at that reaction, at the top there are 3 moles on the reactant side. You've got 2 moles of A and you've got 1 mole of B. Right? On the product side, there are 4 moles. So you've got 1 mole of C and 3 moles of D. Okay, so we've got 3 on the left and 4 on the right. So the side with the most moles is the product side, and the side with the fewest moles is the reactant side. So if we increase the pressure on this system, the position of equilibrium will shift to the left. Okay, it's going to go towards our reactants. This is because there's 3 moles of gas on the reactant side, and they occupy less space than the 4 moles on the right. So it's going to favour the backward reaction, okay, to try and reduce that pressure again, to try and oppose the change. So remember Le Chatelier's principle that states that the position of equilibrium will shift to oppose the change. So in this case, we will get less product. Right? So if this was an industrial reaction and we were trying to get C as our product, if we increase the pressure too much, we're going to favour our backward reaction, and therefore the yield of C would go down. So that wouldn't be a good thing. This comes up a lot in exam questions. So understanding pressure changes in a reversible reaction is really important. So do go back and listen to this slide again. It's all about the number of moles on either side of the reaction. And increasing the pressure will favour the side with the fewest moles. Alright, so I'm not going to read through this too much. This is just a slide about pressure, and it's basically summarising in a table what we've just talked about. Okay, what I would do is I'd pause the video now and make a copy of that table in your notes. But just also note at the bottom there, if the number of moles is the same on either side of that reaction, so if you've got 3 moles on one side and 3 moles on the other side, then changing the pressure will have no effect on that reaction, because both sides are taking up the same space. So it's going to have absolutely no effect on that reaction. So that's an important thing to note. Quite often in exams, they may try and catch you out with a trick question where the number of moles is the same on either side and nothing would happen. But you would have to explain that. You would have to say there would be no change in the position of equilibrium because the number of moles on either side is the same. Right, changing conditions now for temperature. Right, so we've got a reaction again there. So 2 moles of A react with B to give us a mole of C and 3 moles of D. And it's given us some information. So the forward reaction there is exothermic, and that therefore means the backward reaction is endothermic. Okay, if you don't understand that, then you need to watch the energy and reversible reactions video that we looked at earlier. Right, what will happen then if we increase the temperature of the system? So remember, Le Chatelier's principle states that the position of equilibrium will shift to oppose that change. So we want to oppose a temperature rise. So you've got to think which one of those reactions is going to bring the temperature down. Well done. Right, if you said it's going to favour the endothermic reaction, then you are spot on. Okay. So what's happened here? We've increased the temperature of our system, and we've got two reaction choices here. We've got an exothermic reaction, which gives off heat to the surrounding, gives off energy to the surroundings. So that's going to raise the temperature even more. Or we've got our endothermic reaction, the backwards reaction, which takes in energy from the surroundings and is going to reduce the temperature of our surroundings, so oppose the change. So good. The way we'd explain this would say the position of equilibrium will shift to the left. The endothermic reaction will take in energy from the surroundings. Favouring the backward reaction opposes the change that's been put in place, and we would get less product. Okay, so in this example here, we'd actually get less product. So just to mention with that, we've looked at rates previously, and we've said how rates increase. So increasing the temperature will increase the rate of a reaction, and that is true. But what it's doing here is increasing the rate of both the forward and the backward reaction, okay, based on collision theory and based on those particles having more energy, colliding more frequently with the activation energy, okay. But when we've got a reversible reaction, the temperature change, it will favour one reaction over the other. So in terms of our concentrations of reactants, when we looked at equilibrium, we looked at how at the point where the rate of the forward and backward reaction is the same, it's not always that the concentration of reactants is the same. So what we've done here, we've increased the forward and the backward reaction, okay? We've increased the rate of those, but at equilibrium, the rate of those reactions is the same still. All we've done is we've favoured our endothermic reaction, so the concentration of A and B will be slightly higher than it was before the temperature was risen. Again, another table here just to summarise those changes. So something we didn't talk about on that previous slide. So you do need to check whether the forward reaction is exothermic or the backward reaction. Okay, it's not always going to be the case where it's exothermic on the forward and endothermic on the backward. It could be the other way round. So that is what you've got to check. And then if the forward reaction is exothermic and we decrease the temperature, okay, so if our forward reaction, like in the example there, is exothermic and we lower the temperature, remember exothermic reactions give off energy to the surroundings, so they're going to warm the surroundings back up again. So it's going to favour that exothermic reaction so that it all warms up again, and the position of equilibrium will shift to the right and you'll actually get more product. Okay, the table here is really useful, like it was for the gases and pressure one, so do pause the video to take a copy of that. Right, changing conditions, catalysts. So we've got the same reaction here, 2 moles of A plus B gives us a mole of C plus 3 moles of D. So if we use a catalyst in the system, remember Le Chatelier's principle states the position of equilibrium will shift to oppose a change. Now we've not really changed anything here, we've just added something in. Okay, so the catalyst will speed up both the forward and backward reaction. So the position of equilibrium won't change. Okay, there is no shift in that position of equilibrium. What happens here is that position of equilibrium is reached much more quickly. All right, so it's not that we're going to be favouring one reaction or the other. The catalyst affects both the forward and the backward reaction. So that position of equilibrium is reached much more quickly, okay? But the overall yield, the amount that you make, is still the same. The only way that we can affect yield is by changing the concentration, the temperature, or the pressure. Okay, a catalyst does not affect yield. So in an exam, you may be asked to justify the conditions that you use for a reaction. You more than likely will be. So we've got an example here. In industry, methanol is produced by reacting carbon monoxide with hydrogen. So I want you to write a balanced symbol equation to represent this reaction. So first of all, you might need to go and find out what the formula for methanol is. Right? You should know the formula for carbon monoxide. We did mention carbon monoxide in the early video on collision theory, and you should remember that hydrogen is diatomic. Okay, so that means it goes around in pairs. So with that information there, try and write a balanced symbol equation for the reaction. If you pause the video and have a go. Good, well done for having a go. Hopefully you've got the right answer here. So carbon monoxide, CO, is a gas plus 2 moles of hydrogen as a gas in our reversible reaction gives us the methanol, sorry. Methanol is only 1 carbon, so that's methanol. Right, the reaction conditions are there. So it's 250 degrees Celsius this happens at, and 100 atmospheres. And it's showing that the backward reaction is endothermic. So explain what happens to the yield of methanol if a temperature higher than 250 degrees Celsius is used. So we're trying to make methanol, and someone in the company has come along and said, well, let's do it at a higher temperature. Okay, surely increasing the temperature will give us a higher rate of reaction and we'll get more. Okay, but that's not the case, right? We'd actually end up with a smaller yield because remember, if we increase the temperature, Le Chatelier's principle says that the position of equilibrium will shift to oppose that change. So the only reaction that will bring that temperature back down is the endothermic one, the one that takes in energy from the surroundings. So that's going to favour our backward reaction. So our position of equilibrium will shift to the left, favouring our backward reaction and actually giving you a smaller yield. You'd end up with more of your reactants than your product. So it says a pressure of 100 atmospheres is used instead of normal atmospheric pressure. The higher pressure gives a greater yield and a greater rate of reaction. Explain why. So there's 2 things you need to do here. You need to explain why it's going to give a greater yield. Then you also need to explain why it will give a greater rate of reaction. So have a go at that now. Well done if you're getting these right. You know, this is a higher level stuff. So if you're getting these spot on, you're doing really well. Right, so dealing with the yield first. So if we look at our reaction, we've got the gases there. We've got 3 moles of gas on the left-hand side and only 1 mole of gas on the right-hand side. So in terms of occupying space, the volume that those 3 moles on the left will occupy is a lot more than it was 3 times more than the volume that the mole on the right will occupy. So the right-hand side occupies less space. So the higher pressure gives a greater yield because it's going to favour the reaction that makes something that takes up less space. So that's going to favour our forward reaction. Okay, so equilibrium is going to shift to the right because that's the side with the fewest moles, and we'll get more product. Okay, in terms of the rate, so if we increase the pressure, what we then do is we have more particles per unit volume, and therefore there's more collisions per unit time, and therefore the rate is much faster. Okay, another question here. In industry, ammonia, NH3. NH3, you should know what that is by the end. Certainly by the time you go into your exams, you should know that ammonia is NH3. So it's produced by reacting nitrogen and hydrogen. So remember, nitrogen and hydrogen are both diatomic, so they both go around in pairs, and they're going to be gases, and then you're going to make this ammonia gas. So have a go at writing a balanced symbol equation to represent that reaction. So pause the video now. Good, spot on. This is the HABER process, something that you'll learn a lot about, a little bit in the course now, but also when you look at using resources. So explain what happens to the amount of ammonia at equilibrium if the pressure is increased. So pressure, we need to look at the number of moles of gas on either side. So on the left-hand side, you've got 4 moles, and on the right-hand side, you've got 2 moles. So have a go at answering the question. Super. Right, yield increases. Right, if the pressure is increased, it's going to favour our forward reaction. So the equilibrium is going to shift to the right because there's fewer moles on the right-hand side. They take up less room. Okay, so we'll get a higher yield if we increase the pressure. The HABER process uses a catalyst, an ion catalyst, to speed up the rate of reaction. Explain how it does this. So try and do that now. Super. Hopefully you're getting to grips with this now. Whenever it asks you to explain how a catalyst works, you need to say it provides an alternative pathway with a lower activation energy. Though that's the key #1 sentence about explaining what a catalyst does. So a greater proportion of particles have sufficient energy to react. Right, another question here. This is an extended response. That's the end of the course there, the end of the rates of reaction. Hopefully you'll come back and join us for our next topic.